building we have chosen is the Pathe Schouwburgplein cinema building, situated in the heart of Rotterdam. The building is surrounded by the large square named Schouwburgplein and has been a unique landmark ever since its opening in 1992. Under the entire square in the building there is a parking garage. The building is placed on top of this parking garage, therefore it has been constructed lightweight. The building is composed of a set of large boxes, in which the cinema halls are positioned. These boxes are well insulated and they are standing on a grid of columns. The envelope is made of translucent PVC panels. It encloses a foyer, which is a large open space connecting the cinema halls. The foyer is a different climate zone. We have chosen a fragment of the east facade. Our chosen fragment of the facade receives direct sunlight only in the morning. After analyzing the building, we have found some problems with the current structure. Due to a very bad facade insulation, the foyer tends to overheat in the summer. And in the winter, the foyer requires a lot of heating due to the large energy loss. The PVC facade has many disadvantages. It's not an airtight facade, filth sticks quick due to its corrugated shape, and it can easily be damaged. Can we create a more energy efficient climate system and offer a better climatic comfort for the Pathe building in Rotterdam using an integrated system of a lightweight and transparent double-skin facade which provides sun shading and generates energy? Our first reference is the Media ICT building in Barcelona. We have chosen this building because it has a relatively lightweight double-skin facade. It consists of an outer skin facade of ETFE cushions. It also uses two different integrated systems of sun shading. In the first sun shading system, cushions with different compartments are used. Onto the inner and outer layer an opaque pattern is printed. When the pressure in both compartments is equal, the patterns will not overlap and the sun can pass through. This can be done in winter. In the summer, the pressure in the cushions can be changed so the sun can be completely blocked. The southwest facade makes use of a different sun shading system. In the winter, the facade can be transparent. In the summer, fog can be blown into the cushions, which can block a large part of the sunlight from entering the building. The second project we analyze is the Unilever headquarters in Hamburg. We chose this building because of its double-skin facade and its sustainable climate system. In this section we will discuss the climate system. An underground air inlet is used to utilize the constant ground temperature to either preheat or pre-cool the incoming air. The air is brought into the office floors mechanically. Windows can be opened to provide some additional natural ventilation. The used air is passed through the heat exchanger in the roof of the atrium. Now we will take a look at the double-skin facade in detail. The outer skin of the double-skin facade is made of a single layer of ETFE foil. The inner layer is the insulating layer. The outer layer blocks the heavy wind loads, which enables windows to be opened in the inner skin. Sun shading is placed in front of the inner skin layer. Since we have a large square in front of our Pathe building, we will now look at a system that utilizes this large surface to generate energy. In the surface of the asphalt, pipes through which water is pumped are integrated. In summer, the water in the pipes inside the asphalt will heat up due to sunlight. This warm water will be pumped to an underground thermal energy storage. In winter, the outside air will cool the water in the pipes in the asphalt. This cold water is stored in the underground thermal energy storage as well. The hot water that was generated in the summer can now be pumped up to heat the building. This is our climate system design proposal. First we discuss the working of the climate system for the summer situation. Continuous lines stand for water flow and dotted lines are air flows. In the surrounding square around the building we would like to integrate an asphalt collector. The heat pump is an essential part of the energy flows in the building. The heat pump regulates the flows by directing either warm or cold, air or water flows inside the building. Hot water from the asphalt collector can be used to warm water up, which can be utilized for heating the building. It could also be stored to use it later. The heat pump is connected to an underground thermal energy storage system. These two work together to store excess hot or cold water deep underneath the ground. The heat pump is connected to pipes that are integrated in the floors of the cinema. Through this concrete core activation system, either hot or cold water can be pumped to heat or cool the building. For the ventilation of the building, we use an underground air inlet to suck in air through a pollution filter from outside into the building. By sucking in air underground, we use the constant ground temperature of around 13 degrees to either heat or cool the outside air. The cinema halls and foyer need mechanical ventilation. The air comes from the heat pump. We use a double skin facade system. The outer layer will consist of ETFE cushions, similar to the southwest facade of the Media ICT building. Via openings in the facade, air will flow in between the layers. This air will heat up due to the sunlight and will rise to the top of the facade. Due to the rising of hot air inside the facade, a draft will occur. This draft will be utilized to naturally suck out air out of the foyer. The used air from inside the building is fed through the heat exchanger. Here the energy out of this air will be exchanged to water, which will be pumped back to the heat pump. This thermal energy can be then reused in the building. This is the resulting total climate system for the summer. In the winter the system works roughly the same, except that some air or water flows on an opposite in temperature. A bigger change, however, is in the double skin facade. The facade can be closed off during winter, creating a facade that is very insulating. The heat that is still formed in top of the facade can now be fed into the foyer of the building. The black lines illustrate the systems that are either used for heating or cooling, due to the average temperature in the mid-seasons. The double skin facade is opened and air can now freely flow inside and outside the foyer.
For the individual design, I will make a double skin facade with an outer layer of a single ETFE foil and inner layer of glass. The construction will be a space frame of steel cables.
In my personal design, I would like to use a tension cable nut structure. This system consists of tension cables to which an outer layer of ETFE cushions and an inner layer of double glazing is connected. This creates a very transparent and lightweight facade.
Ultra lightweight is the main idea of my personal redesign proposal. For this reason, I chose carbon fiber as a material for the facade construction. The new structure will be designed as a double skin facade with an insulating interior layer made of polycarbonate glass and a three-dimensional outer layer made of transparent polycarbonate windows.
I will develop a double skin facade with an outer layer of ETFE cushions, an inner layer of double glazing and a supporting structure made of wood.